Welcome to Linear Programming. This is part of a Modelling with Algorithms course, but it's also covered on many decision courses for A-level further mathematics. Today we're going to be introducing this topic. We're going to look at a graphical approach to linear programming, specifically a two-dimensional case, and we're going to go right from the basics. So the first question is, well, what is linear programming? Well, the idea with linear programming is we are to maximize or minimize some function of x and y. It's a two-dimensional case, just two variables, x and y. We often call it p for profit, but it doesn't have to be p. And a and b would be numbers. Okay, it's a linear programming problem, which means everything you're going to see is linear. This is going to be a linear function to maximize or minimize. Okay, so that's the objective. That's what we're trying to do. But alongside this objective, we have a series of constraints, and we say that this maximize, this objective function, is subject to, and then we have a number of linear constraints which will tend to be inequalities. So linear constraints. And I say tend to be inequalities because when you get to higher than 2 dimensions, you can have equations which are constraints as well. Okay, but for the two-dimensional videos, that's this video, the next 4 at least, there'll all be inequalities because otherwise it'll be a one-dimensional case, which is just solving an equation. Okay. All right. So let's have a look at what one of these might look like. So I've got 2 examples to do in this video, and I'm going to run them through from start to finish. Okay. So the first question is we're going to maximize p. Which equals x plus 2y, so that's our objective function, subject to, and then we have 5 constraints. We've got these 3 linear ones, and then we have these 2 which just stipulate that x and y can be non-negative. Okay, so this is the objective function. This is actually the bit of the linear program that we look at last. Okay, we look at the constraints first. Okay. Now the idea is we graph these constraints. That'll give us a region where x and y values will satisfy all of these constraints, and that is described as the feasible region. Once we've got the feasible region, we then look at all the vertices of that feasible region, and we compare those vertices with the objective function, and then we choose which vertex maximizes, in this case, our value of p. Okay, so that's the idea. So to graph these, what we're going to do is first of all decide at what points these all cross the axes. And that's important because we need to know how big to draw our graph. Now, occasionally there will be a graph already drawn for you, but both of these examples in this video will be drawing the graphs from scratch. Okay, so the best way to decide how big you need to draw the graphs is just to consider where these cross the x and y axes. So if x is 0 on this one, then y is going to be 21. And if x is 21, then y is going to be 0. I'm just pretending that's an equal sign for a minute. And we're going to draw this linear line, and then we'll decide which side to shade. The second inequality, when x is 0, y would be 75 on 5, which is 15. And when y is 0, x will be 25. And then finally, this third constraint, when x is 0, y is going to be 10 and a quarter, 10 and 2/8. And when y is 0, x is going to be 82. Okay, these are just the axes, so we can actually ignore those for now. Okay, so that tells us that in the y direction, we need to go up as far as 15. Nope, 21. So that's the highest value in the y direction, 21. And then in the x direction, we need to go up as far as 82. Okay. All right. So now I come to draw my graph. Okay, I need to go up as far as 21 in my y direction, and as far as 82 in my x. Okay. So I'm going to get my ruler out. I'm going to call that, let's call that one there 20. And just so I can fit it all on the screen, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's going to be 0 down there. Okay, so we can see the whole graph on the screen. Okay, so there's my y-axis. And then my horizontal axis, that needs to go up as far as 80. So let's do 10, 20, 30, 40, 50, 60, 70, 80. Yeah, that'll do. Obviously 82 is slightly more than 80, but not by much. So x-axis. Okay. So plot some points. 1, 2, 3, 4, 5. That's 10. 1, 2, 3, 4, 5, 20. Good. 10, 20, 30, 40, 50, 60, 70, and 80. Do notice that the scales on both axes aren't the same, and that's absolutely fine. They don't have to be the same. Now, in an examination, you won't have access to all these multitude of coloured pens, but just for this video, I'm going to colour code these constraints so we can see which one is which. Okay. So this first one is going to go from x on the y-axis is x is 21 on the x-axis, and then 21 on the y-axis. So we're going to have 21 is that point there on the y-axis, and 21, well, that's 25, so it's going to be about there. Okay. Doesn't need to be 100% accurate because we will be using algebra to solve any intersections, but you do need to get fairly accurate to get the full credit for this one. Okay. And I'm also going to label this graph as well. So I'm going to say this is x plus y currently equals 21. Okay, we'll do the shading now. So it's not equal to 21, it's less than or equal to 21. So the best way to decide which side of the line to shade for this inequality is to plug in the origin. So does the origin satisfy this inequality? Well, 0 plus 0 is less than 21. So yes, the origin does satisfy it, which means this side of the line is the side that we want. Now, in linear programming, you shade the side you don't want. And we don't have to go overboard with the shading, just some hashes on the back of the line is enough of the shading. I don't want to see big scribbles all over the page. That just looks messy. That is a perfectly well shaded line for linear programming. Okay, so that's this first inequality. And I'm going to repeat that for the next two inequalities. So we're going to go to 25 on the x-axis, to 15 on the y-axis. Nice straight line. Get my ruler out. There we go. Label it. So this is 3x plus 5y equals 75. And then again, check if the origin satisfies it, which again it does. So I want the side of the line with the origin, which means I'm going to hash the side that is on the other side to the origin. Final inequality, got 10.25 on the y-axis and 82 on the x-axis. So 82 is going to be about there, and 10.25 is going to be about there. Again, join them up with a straight line. Like that. The origin again satisfies this inequality, so it's the top shot side of this line I'm going to shade. So that leaves these other two inequalities, which is just that x and y can be non-negative, and so that is going to be the opposite sides of the axes. So that is now my shaded region. Anywhere that's on the shaded side of a line, it is going to, that coordinate x and y is not going to satisfy at least one of these constraints up here. The region, which in this case is in here, this region, pairs of values of x and y satisfy all the constraints. So these are all possible values for the problem, or if you like, they are all feasible values for the problem. Which is why we refer to this region as the feasible region. Sometimes shortened to FR. I'm going to say FR equals the feasible region. So any point, any x value, any x, y pair in this feasible region satisfies all 5 of these constraints. Now, of all these infinite pairs that we have inside this region, one of them will be the solution to the linear program. This is where we start to look at the objective function again. Now, a property of linear programming, it's only true for linear programming, is that the optimal solution, so the pair of values for x and y which will maximize this objective, will lie at a vertex. So we've got one vertex there, one vertex there, one vertex there, one vertex there, and we've got the origin down there. Okay, so we've got 5 vertices for this feasible region, and one of these 5 points will maximize the objective function. Okay, so it's our job to decide which one it is. So to do that, we are going to find the coordinates of these 5 points. So I'm just going to call them A, B, C, D, and O, just so I can refer to them. You don't actually have to include O because it's a maximization problem, but I tend to just for completion. Okay, but you don't need to. Okay, so the point A is going to be where this green one intersects the y-axis. So we can see that is already calculated at 0, 10.25. So the coordinates of A are 0, 10.25. Okay, the coordinates of B, that is the intersect of the green line and the blue line. Okay, so if we change this to an equal sign, we're going to solve these equations simultaneously, which you can get the calculator out for if you choose to, but I'm not going to spend time solving these equations simultaneously. I'm just going to state what the point is. In this case, the point B is the point 10, 9. Okay, just check that kind of makes sense with the graph. Okay, 10 on the x, 9 on the y. It looks about right, but you shouldn't use the graph to decide the point. You should solve it algebraically. Okay. Okay, the point C, that's the intersect of the green and the orange line. So that is going to be the intersect of the top and bottom. And again, I'm not going to solve them on here. Okay, check out other videos for solving simultaneous equations. C is the point 15, 6. 15 in the x and 6 in the y. Okay, so the graph isn't great, but we'll go with it. And then finally, the point D is down here on the x-axis. Well, that's got 21 on the x and 0 on the y. And I should include the origin for completion, but you wouldn't lose marks if you didn't. So these are the 5 vertices of my feasible region, and the optimal solution, that is the solution to this objective function, will be one of these 5. So to decide which one, what we're going to do is we're going to take each of those coordinates in turn and plug them through the objective function. So the first one is x is 0 and y is 10.25, and the objective function is x plus 2y. So I'm going to take the value of x, which was 0, times it with 1, plus 2 times the value of y, and the value of y at the point A was 10.25. Okay, so that is 20.5. So that is the value of p at the point A, 20.5. And I repeat that process for the other points as well. That's obviously 0. So that is 21. 15 plus 2 times 6 there. That's 15 plus 12. That's 27. And then I've got x plus 2y, so it's 10 plus 2 times 9 is 10 plus 18, which is 28. Okay, so these are the 5 values of p at the 5 vertices of my feasible region. And then just check, I want to maximize the value of p. So which of these is the biggest? Well, it's 28. So therefore, that is the solution I want. Conclude then the linear program with my answer to the problem. The maximum value of p, subject to the constraints, is equal to 28. And that occurs when x equals 10 and y equals 9. This is the solution to the linear program. This is the vertex testing. This is the drawing of the constraints. And this is the linear programming problem originally. Okay. In theory, you could be asked a question like that, just maximize this subject to these constraints. might be 6, 7 or 8 marks or so. And this is exactly the process that you would be expected to do if it asks to solve it graphically. Okay, got one more example for this video, and then the next video we're going to have a look at solving a minimization problem. Okay, so another problem. Maximize p equals 6x plus 5y, subject to, and then we have 4 constraints this time. But we don't have any origin constraints. Okay, so exactly the same as before. I'm going to find where these cross the axes. 2y equals x, well that's just the gradient, y equals a half x, so that's just going to go through the origin, so I don't need to worry about that one yet. I'm just going to mark that as orange and then come back to it later. This one here, this one's going to cross the y-axis at 8. It doesn't cross the x-axis at all because it's a horizontal line. The next one, when x is 0, y is going to be 60 divided by 4, which is 15. And when y is 0, x is going to be 60 divided by 3, which is 20. Okay, so those are the 2 coordinates there on my x and y axes. And then this one here, when x is 0, y is 20. And when y is 0, x is 20. Okay, so it's going to cross 20 on both axes. So I need to go up to 20 on my x-axis, and I need to go up to 20 on my y-axis as well. So this time I'm going to have the same scale on both of my axes. Okay, so 20 in both. Okay, so let's say that's 20 there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's put 0 there. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's put 20 there. Drawing my lines, my axes. There we go. So that's my x-axis going that way, and my y-axis going vertically upwards. I'm just going to mark 10 as well. Okay. Right, so I'm going to plot all of these now. So let's start with the orange one, which was essentially y equals a half x. It's going to be there. When x is 10, y is going to be 5. When x is 20, y is going to be 10. That's going to look something like that. You only need 2 points to draw this linear line. Obviously, in this situation, you can't put 2 points on each axis and join them up because it only goes through the origin on the axes. So that's that one. And now, to decide which side of the line to shade, choose a point. Now, up until now, we've chosen the origin, but if you plug the origin in, that's not going to be helpful because in this case, the origin lies on the constraint. So we need to choose another one. So let's just choose 10 on the y-axis, which has coordinates 0, 10. Let's plug in 0, 10 into here. I get 20 is greater than x. That is true, that is satisfied because x is 0. So therefore I want this point in my feasible region or feasible side of this line. So I'm going to hash out this side. And if you chose a point on the other side of the line, so for example, let's choose x is 10 and y is 0, and plug that in here, then I'll get that 10 is less than 0, which is not true. Therefore, I do not want this point. So again, hash out this side. Essentially, all of the points this side of the line do not satisfy the orange constraint, and all of the points that side of the line and on the line do satisfy that constraint. Okay, the blue one here, y is less than or equal to 8. This only goes through the y-axis, doesn't cross the x-axis at all, and that's because it's a horizontal line. So it's easy to draw. Oh, I didn't label my orange one. That's 2y is greater than or equal to x. This one is y is less than or equal to 8. So therefore I'm going to hash out the top because I want values to be less than or equal to 8. So I'm not interested in anything above that. The next one, we're going to go from 20 on the x-axis to 15 on the y-axis. So 20 on the x is here, 15 on the y is here. Join those up with a straight line. The origin doesn't lie on this one, so I can throw the origin in and see if it's satisfied. 0 plus 0 is greater than 60. That is not true. So I don't want the origin because the origin does not satisfy this inequality. So therefore I'm going to shade the underside of the line. And then I've got one more constraint to go, which is this one. It goes from 20 on the x to 20 on the y. Like that. Those up like so. And again, decide which side of the line to shade by throwing in the origin. 0 plus 0 is less than 20, so the origin is satisfied. So therefore, I do want the origin. So I'm going to shade the upper side of this line. This was x plus y is less than or equal to 20. And the green one, which I also haven't written in, is 3x plus 4y is greater than or equal to 60. Okay, so there is my graph of my 4 constraints. Notice that the origin does not, the axes do not bound the feasible region, which is possibly why they're not included in this list, but sometimes they're not included and you just assume them to be true anyway. Sometimes it's irrelevant if they're true or not. Okay, so deciding the feasible region is a bit more complicated this time because it's hidden away in one of these areas. But this area in here, this little quadrilateral, this is the only area where there's no shading on any side. So therefore that is the feasible region of these constraints. Okay. So a bit smaller than the last one. I'm going to call that A up there, B there, C there, and D down there. And just like before, we are going to list those 4 points and then decide which satisfies the objective function. Okay. So A, that is the intersect of the green and the blue lines. So clearly y equals 8. And then if you plug that into here, you'll get a value for x. X comes out to be 28/3 and y is 8. Okay. Notice that now we've got some fractions kicking around. That's fine, just roll with it. Okay. We're A-level maths, we can deal with fractions. The coordinates of B are the intersect of the red line and the blue line. So again, y is going to be 8, but this time x is going to be 12. So the coordinates of B are 12, 8. The coordinates of C, intersection of the red and the orange. Okay, so mathematically I'm going to be solving these simultaneously. And we end up with C is the point 40/3, 20/3. And then finally the point D, that's the intersection of the orange and the green. So solving these two simultaneously. And if you do that, you'll get the point 12/6. Okay, so those are the 4 coordinates of the 4 vertices of my feasible region. Okay, now at this point, I take these 4 points, which I've extracted from the graph, and I'm going to run them through my objective function, which is p equals 6x plus 5y, and then I'm going to choose the biggest, so value of p. Okay, so at A, so 6x plus 5y, we're going to do 28/3 times 6 plus 5 times 8. So the value of p at the point A is 96. And repeat that process now for the other 3 points. So 12 times 6 plus 5 times 8 is 112. This one here, we're going to do 40/3 multiplied by 6 plus 20/3 multiplied by 5. That's 340/3. Just to get a numerical value for that, we're looking at about 113. That's winning so far. Okay. And then finally, point D, which is going to be 6 times 12 plus 6 times 5. It's 102. Okay, so our objective was to maximise. this value of p, so looking at the 4 values of p that we have obtained, this is the biggest. So the solution then to the linear program is the maximum value of p, subject to the constraints, is 340 thirds. And this occurs when x equals 40 thirds and y equals 20 thirds. Okay, so that's the solution to the linear program. Here we have the vertices being checked against the p-values. Here's our graph of our constraints and the feasible region, and there was our original linear program. Okay. In the next video, we're going to have a look at a minimization problem. It's exactly the same kind of procedure, but minimizing p instead of maximizing. All right. Thank you very much for watching.